So today we're talking about kinematic graphs and constant acceleration. Displacement versus time graphs. So in displacement versus time graphs, the vertical, the axis that goes up, is displacement, which can be labeled x. I know it's counterintuitive that the y-axis is going to be labeled x, but that's what it is. X is not representing a direction in this case. It's representing displacement. So the horizontal axis can be labeled as t, which is time. All right. Now time is usually measured in seconds, but it could be measured in minutes, hours, anything like that. But usually what we end up with is meters and seconds. So because the y-axis is displacement and the horizontal axis is time, or slope, which is the vertical axis over the horizontal axis, is going to be displacement over time, which is velocity. So slope equals velocity. Sections of the graph with a positive slope going up, like point A has a positive slope, has a positive velocity. Sections of the graph with a negative slope, or going down, like point C, have a negative velocity. That's right. Sections of the graph with a flat line, like B, you notice the top of that arc right there, it actually has a slope of 0 at the top. So sections of the graph where the slope is 0 have a velocity of 0. Now an intersection, if we had more than one line, would mean that at that particular time, both objects have the same displacement. So the red object has a positive velocity, stops for a second, and then has a negative velocity. The green object has a constant velocity, constantly increasing velocity. Now, the slope is velocity, but the point, the actual point, gives you displacement at a particular time. So at point A, which would be time equals 0, both objects are at the same place. At point B, at that particular time, both objects are in the same place again. Okay? So intersections on the graph means that both objects have the same displacement. Velocity versus time graphs. Velocity versus time is slightly different. The vertical axis now means velocity, which can be labeled v, and is usually meters per second. The horizontal axis is time. Now, time is labeled t, and is usually in units of seconds. Now, in this case, any point that you have is your velocity at a particular time. Slope, which is the movement in the vertical axis over the movement in the horizontal axis, is now change in velocity over change in time, which is acceleration. So sections of the graph with a positive slope, like the green line, have positive acceleration. Sections of the graph with a negative slope, like the red line, have negative acceleration. And sections of the graph with a flat line, like the yellow line, have a slope of 0, and therefore has an acceleration equal to 0. Usually for this level of physics, we won't have changes in acceleration. So velocity versus time graphs will usually have straight lines on it. Intersections mean that at a particular time, both objects have the same velocity. So at this point, whatever time this is, the green object and the red object both have the same velocity. At this point here, the red object and the yellow object have the same velocity. So that's what intersection means for velocity versus time graphs. Graphs for a ball thrown in the air, or any object thrown in the air for that matter. All three of these graphs represent the same movement. Okay? Now, if you look at the displacement, if you trace the trajectory of the ball being shot in the hoop, basically having the y direction as your displacement, as time goes on, it goes up, it slows down, and then it goes down. The velocity of this basketball is changing with each second, and it's a constant change. Although the position goes up, the velocity is actually decreasing the entire time. So it's slowly decreasing until it gets to 0, and then it increases in the negative direction. So it constantly gets more and more negative. This constant change in velocity is called acceleration. And you'll notice that with the acceleration graph, we have a constant acceleration because it's acceleration versus time, which is denoted by that flat line. Now we don't have anything for rate of change of acceleration, so the slope on the acceleration graph isn't going to mean anything to us. As a matter of fact, you will usually see an acceleration graph with a flat line because in kinematics we use a lot of situations where acceleration is constant. The value that this graph is flat is negative 9.8, and that is acceleration due to gravity. Okay, so the acceleration due to gravity is always making the velocity change in the negative direction. So if it's already falling down and it changes in the negative direction, it's going to fall down faster. If it's going up and it's changing in the negative direction, it's going to get slower until it gets to 0 and then come down. Relative velocity. This is defined as the velocity of one object relative to the other. The ground is usually what is used as a frame of reference for velocity of an object. Objects that move in the same direction appear slower in reference to each other. You're going to subtract velocities. Objects that move in opposite directions appear faster in reference to each other. And so you would add velocities. Okay? Now, the only difference between relative velocity and the velocity that we know and use when we drive and run and do all that stuff is that the ground is used as a frame of reference for the regular velocity. For relative velocity, two objects are used as frames of references. A moving object is used as a frame of reference. So let's think about this. You're in a car traveling 10 meters per second, and you're going to crash into a car going 5 meters per second. Now, that doesn't tell the full story because I don't know if you're moving in the same direction or in opposite directions, all right? So which situation would you rather be in? Would you rather the other car travel in the same direction you're going when you crash? Or would you rather it travel in the opposite direction? Now, if you really think about it, which case does the other car have the greater relative velocity? If I have to be in a crash, I would rather crash into a car that's going the same direction as me. That would soften the impact rather than if the car was coming at me in the opposite direction. Right? So, in which cases does the other car have greater relative velocity? When it's traveling the opposite direction. What is the relative velocity in both cases? Well, in the case of them traveling in the both directions, you would subtract. And 10 minus 5 would be 5 meters per second. So the relative velocity of the other car would be negative 5 meters per second. If the car was coming at me and I tried to calculate the relative velocity, it would appear to be moving faster. So I would add it up and it would be 15 meters per second coming towards me. Average velocity. Equation given two displacements. The average velocity is going to be change in displacement divided by change in time. Change, that triangle, delta x and delta t. Delta usually means final minus initial. So delta x will be final position minus initial position. If you're given two velocities and you have constant acceleration, your average velocity is going to be those two velocities added together divided by 2. Same thing as average anything. Whenever you take the average of something, you add up your numbers and you divide by the number of numbers. So average velocity, you add up the two velocities and then divide by 2. So we also have constant acceleration equations. These equations only work when the object is undergoing a constant change in velocity, or you could say acceleration, constant acceleration. Here are some steps to how to do a constant acceleration problem. You're going to fill out what is called a VVDAT table. I'm going to show you that table on the next slide. It basically stands for initial velocity, final velocity, displacement, acceleration, and time. You're going to pick the equation that's missing what you don't care about. Now it sounds like a double negative. The variable you don't care about is 1, not given in the problem, and 2, you don't need to find it. So you're going to pick the equation based on that. Now if you look at these 4 equations, let's say that you're not given time and you don't need to find it. Well, if you're not given time and you don't need to find it, then I'm going to pick the equation that does not have time in there. And that would be the 4th equation. The 4th equation does not have time in there, delta t. As another example, let's say we do not have and do not care about final velocity. Well, the first equation has final velocity. The second equation has final velocity. The third equation does not have final velocity. So if I'm not given final velocity and I don't need to find final velocity, I would use the third equation. Alright? Your third step would be to just solve for your missing variable. Let's take a closer look. Here's our VVDAT table. The variables in the table are defined as follows. VI is initial velocity, VF is final velocity, D is displacement, A is acceleration, T is time. Now here are some common assumptions. If you start from rest, rest means 0. That means your initial velocity is 0 meters per second. If the object stops, which means you were moving and then now you're not moving, that means your final velocity is 0. Both of these won't happen at the same time. If object is in the air, or you're saying free fall, then your acceleration is negative 9.8. Now if it's not in the air, you cannot assume this acceleration. You either have to use the acceleration given or you'd have to find acceleration. If the object has a constant velocity, that means A is equal to 0. So here's an example. A boy sledding down a hill accelerates 1.6 meters per second squared. So we have acceleration. If he started from rest, which means we have initial velocity, in what distance, they want to find displacement, would he reach a speed of 9 meters per second? That would be your final velocity. Let's break it down. Accelerates at 1.6 means A is 1.6. Started from rest means V is 0. In what distance means you're looking for D. A speed of 7.0 means final velocity is 9.0. And which variable do we not care about? Which equation do we use? Now once we fill this out, you'll notice that we have initial velocity, final velocity, we are looking for displacement, we have acceleration, and we do not care about time. So since we don't care about time, we're going to use the equation that does not care about time, and you are going to solve for delta x.